Good evening and welcome to webinar 2. I am Dr. Ken Mahler. We're going to be talking about topography tonight. Thank you for joining us. The topic today is really the interpretation of our topographies even before we start designing up a wave lens. So a couple of little bookkeeping things here. I am a consultant for Oculus and for Wave. My practice is a solo private practice. It's really a contact lens only practice. I have no spectacles. I don't really do any disease other than anterior segment, and it's really focused on irregular corneas. I have done national clinical support for Wave before. That was helping on case-by-case basis. I've done lectures for Wave, which is formal instruction on how to utilize Wave and apply that in clinical practice. I also do offer private practitioner consultation services, and there's a couple of modes of that, and I will go over that on a slide near the very end of this presentation tonight. I am a beta tester for the software and helping develop the Wave and the CSP software. I did design up the very first Certified Wave Designers program, and I'm currently involved in guiding the Wave training. All right, so let's get to Wave. What is it? Well, that's a really good question. A lot of people think Wave is a lens. Some people think it's a piece of software. It really is an interface, and that's all it is. It's a software interface that lets a physician talk to a lathe to design what's necessary to be manufactured. And how does it work? Well, it really talks a language that we as doctors understand rather than the manufacturing side, and it translates what we understand into what can be manufactured on the lathe side. Wave is basically a modeling system, and it takes a data stream that's been collected from some topographical device. It creates a digital mold to create a template of that surface, and it gives us now a base to design that lens from. So the process really is the cornea, which is the truth, speaks to the topographer, which alters the truth a little bit because all topographers make certain assumptions when they're collecting data. Topography then talks to Wave, and Wave actually alters some of the data that comes in from the topography to make it more palatable for us to design a lens from. And then we take Wave, manipulate certain things on that, and turn that into a lens design. So let's talk a little bit about the interpretation of topography before we start designing up a Wave lens. Understanding this data collection process is very, very important to really understanding if you can really utilize this data, and if you can utilize it, what caveats may come along with that. So there's basically 3 steps to this particular process. The first one, step 1, is the topographer's access to the cornea. And most of that I did cover in webinar 1, and I'm going to just briefly review that tonight. Step 2 is the actual capture of the data, and the 2 systems that are currently being utilized are either placido disc-based, which is reflected data off the corneal tear film, or shine fluid camera, which actually does detection of the edge of the cornea to determine where the cornea actually is in physical space. And step 3 are the algorithms that are incorporated in the software itself that process that captured data. And it's really important to understand that this really is this 3-step process before you can design up a lens. Okay, then you have certain displays that you can look at this data, and the 3 that are most relevant to us as lens designers are the curvature, elevation, and refractive displays. Topographers certainly have the ability to display many, many more things about the cornea, but these 3 are really the ones that are most important for us and from the lens designing standpoint. Wave then imports the topography, and we do need to understand how extrapolation changes some of that data that's coming into Wave, because that is not the same as the raw data that was collected right at the corneal surface. We take that imported data stream, we create that digital mold, and then we base a lens design. So we go cornea, topography, to wave, to a lens. All right, so let's start with step one. This is just a very quick review of what I covered in webinar one, and it has to do with the topographer's access to the cornea. If the lid's interfering, that's not giving the topographer good access to the cornea, and we've already talked a little bit about how lids can really alter data. This particular image here on the right was a misaligned capture. You can see here in the upper left that the patient was actually fixating somewhere off to the temporal side over there. And so as a result, all of this data down here on the right is tainted. Next we have, this was actually taken over a contact lens, and you could see all of this debris that's in the tear film. Since this is a placido disc-based system, anything that's reflecting off the tear film that disturbs the tear film is going to disturb the data. Here we just have a bad operator error, and you could see that everything was kind of shaking at the time that this was captured. Over here, we could see, again, on the right eye, the lids are sort of obscuring some of the data, and on the left eye, you might say that's actually not all that bad. We have this down at the bottom. The problem with this data was something entirely different. This is exactly the same set of eyes, both on the top and the bottom. And you could see that the top set of eyes are considerably steeper looking than the bottom set. So what went wrong? What went wrong was when these were captured, they were captured in an improper plane, and so the topographer interpreted the curvatures incorrectly. By the way, the error there is by about a 3 diopter magnitude. So that's a very, very significant error. Okay. What's wrong over here? Well, this was a calibration error. We could see right over here that we had the same exact thing come up on the right and the left eye. And no, I don't think that that's exactly how that particular set of eyes was put together. That was really a calibration error. And so now when the processor, when the topographer processed all the data, it processed that error from the calibration right on through into the topography. This one here is an obviously very steep keratoconic eye, and you have to be very careful once you start getting very irregular eyes. Here we could see on the comparison for the repeatability between all these maps, we have a difference of about 3 diopters of standard deviation on this set of topographies, and so poor repeatability means we have unreliable data. All right, so that's just a quick review on step one, meaning giving the topographer access to the cornea, and we have to give it good access so it has a chance to capture good data. Now, step two is the actual capture of the data, and we're going to start with the placido disc. So here is a capture, and I have just the ring reflected image over here, and let's take a little analysis of what we've actually captured over here. So you could see here at number 1, we have this very widened ring over there. Trust me, the ring didn't look that wide on the actual cone that was reflecting there. That's a reflection error. Here at number 2, we could see here that there's sort of an incomplete ring. It looks like possibly something was floating by in the tear film. Here at number 3, we could see that we have a ring that got pinched over from the inside to the outside ring. Here at number 4, we could see there's a widened band. And at number 5, again, the rings are a little bit crowded over there. So if we process this particular image and take a look, oh, I'm sorry, I forgot that. And here we have absolutely no measured data whatsoever. So if we take a look at how this is processed forward, here's the, this is on a scout topographer, and the extrapolated rings are over there. But let's take a look and see what actually happens. Those reflection errors caused these inconsistency in the rings. So we could see there at number 1. Number 2, we have that little bump out on that red ring. Number 3, you could see where that widened area has created something a little unusual there for the ring image. Number 4, that's that pinched area, and the green and the red have sort of bunched up together. And there at number 5, you could see again another bunching up of the rings, all because of those reflection errors. And then, of course, we have imaginary data out here because we didn't actually capture any data. So looking at the actual map, look and see how the color map now has been affected by these reflection errors. You could see at number 1, there's a stepwise motion. Number 2, the cornea looks very, very flat over there, and that's because of how that ring got spread out. Number 3, we have a divot in the middle of the cornea there. Number 4, you can see that steepened area. There's like a steepened arc. And at number 5, we could see it was heading toward the whites because everything was bunching up. And so it was showing excessively steep curvature there when that's probably more of a reflection artifact than real data. So let's move forward here to dots editing. Dots editing is always a very hotly debated topic. So should we fix the problems with the way those captures were done? So what I did as an experiment is I've gone ahead and I've dots edited these images. And you will see here that I have cleaned up these maps from the jaggies. The jaggies are where you will see in just a couple of slides forward that the rings end up mismatching which ring data goes with which ring capture. And so I went ahead and fixed the jaggies on ring number 17 here by connecting that little blue connector bar there. On this ring, 26, you see I corrected that very, very large area that was going from about a quarter of the cornea over there. And in addition, I've corrected up these additional areas that had all kind of irregular data being displayed, all because of the fact that something was wrong with the original capture. This is a dots editor image where I've gone ahead and since rings 27 and 28 looked so awful, I just deleted them. So now let's go ahead and take a look. It's extrapolated version, and it looks beautiful now because all the rings are perfect circles, just like they should have been on the original capture. We've just gone ahead and fixed that by dots editing these. So these are all the extrapolated rings that have been added in. The 2 inner ones were the ones I deleted, and then those 2 outer ones were just added in because we didn't capture any data there, but we do need that data so we can create a surface for wave to reference. So now let's take a look and compare the original, which is the one on the left, with the dots edited fixed version on the right. You can see on ring 17, I connected that with the little blue area, and you can see that little jaggedy thing where it connected with a ring further outside, thinking that's actually where the ring should have been. On the next ring, 21, you could see we had some more errors over here, and so we have what looks almost like an electrocardiograph there, where we have the blips on the left image, but it's all been cleaned up very nicely on the right image. When we move to the next ring at 23, it gets even worse, but my image on the right is very clean looking. On 24, it's getting considerably worse, and that's very typical that the further out from center you go, the more irregular the data can become. Here's ring 25, and you could see up over here on the top, I'm actually off the screen. It thinks that the connection is somewhere actually almost off the cornea. On 26, again, I'm off the actual screen over there. And then for 27, I deleted this ring because you can see how mistaken getting from this point over here out to over here, it thinks that this is the actual continuity of that particular ring. So we just deleted that on our dots edited image. And the same thing on 28, because here you can see we're missing the entire half of the cornea over here. And so we went ahead and just deleted those and put in proper rings. So now let's compare. Here's the topography that was actually captured. So that's actually the raw data that was captured by the Scout topographer. This here is Wave's interpretation that was not dots edited. So that's the raw data just being fed directly into Wave, and Wave interpreting what the cornea looks like. And for the most part, you could see that cornea is very, very well represented in Wave. This is my dots edited image, and you can see, other than some subtle flattening out over here as compared with over here, these really do look very similar. So despite the fact that I took the time to go ahead and fix all of those rings that looked like they were absolutely horrific, and had very, very erroneous data. By the time it got into Wave, Wave did a pretty good job of fixing that all on its own and creating a pretty good image. And in fact, if you take a look back at the raw topography, you can see that there's a little steepened area over here. This happened to have been a hyperopic LASIK case. And so that's actually the flap junction over there, which most likely is that real data. That's not artifactual data. And if anything, by editing the data here, we've actually made it artificially flatter than it really was when it was in the raw form. So dots editing, from my perspective, is really a total waste of time. You have better things to do. And if you feel that the original image was so bad that it needs to be dots edited, go back and spend time getting better images. Don't take your time and erase data or connect the dots. That really is a total waste of your time. All right, so let's move on. Here's the Shine Fluid camera, and although this uses entirely different technology, by using edge detection technology from a camera, as opposed to the reflected data that the Placido disc uses, it is not immune to capture errors as well. So what happens here is that the software identifies the edges of the cornea. And in this particular image, you could see that there's a red line and a green line. The red line is the edge of the anterior surface of the cornea, and the green is the posterior surface of the cornea. It does a very, very nice job of creating a continuous surface with those red and green lines, and that would be the surface that is then fed into Wave. Now, when there are excessive reflections, such as you can see here on the areas where we're getting out at the limbus and onto the sclera, edge detection does not work because it's the edge is obscured within the very, very bright reflections. So edge detection is a very, very good technology, but it is defeated by very, very strong reflections that are coming off the surface. So where this becomes important is not so much at the edge, but when you have a cornea that has some opacification in it, such as this particular cornea, you can see that the edge detection right here has failed, and the reason is because of the reflection. Over here, we can see this particular cornea has quite a few opacities in it, and the edge detection, once again, has a very, very difficult time trying to figure out exactly where that edge is because of the bright reflection. Certainly, we do expect that out over here at the limbus and onto the sclera because that's much more reflective tissue. But when the cornea has these opacities, that really is very problematic. So when we use the pentacam to do a CSP capture, in order to get the scleral data, what the pentacam does, and this is not manually driven by the operator, this is all done on the hardware side, is that it attenuates the light so it then can actually measure where the edge is. So you could see these are the two edges at the extremes, and it was able to detect the edge very, very nicely all the way onto the sclera. It's just the cornea here is so dim because of the fact that the light has been attenuated. All right, now when we have edge detection problems, you can see here what looks like a polka dot pattern, and those polka dots are all extrapolated data. So in essence, the software has added in data where it was not able to actually measure data. And so if you have excessive reflection off of various corneal opacities, be prepared that you may end up with extrapolated data there if you're using the pentacam to detect the edges. Okay, so now let's move on to step 3. Step 3 is the software algorithms that are contained within that actually do all the processing of this captured data. On this left over here, this is the captured data off of a obvious keratoconic that is done with the Scout. And on the right, this is the exact same eye that was done with the pentacam. The algorithms process what's been captured, and it can create very subtle changes to the raw data. sometimes the changes aren't really all that subtle. Sometimes they're actually fairly significant. And so you do need to be aware of this depending on which instrument you're using to design the lens. So let's take a look for a moment here. And I've just compared on the left and the right by circling the two areas there. And you notice that the curvatures look considerably different on the left and the right. We have that little flattened sort of triangular shaped downward pointing area in that circle on the scout measurement, yet on the pentacam that doesn't seem to be there at all. Up on the top over here, you can see going from top to bottom on the scout, it's steep, flat, and steep, yet on the pentacam image, we can see that it's really just flat and steep. So the data has been changed because clearly this is the exact same cornea. These images were probably taken within 5 minutes of each other. So I know the cornea hasn't changed, and these are both really good captures. These changes that we're seeing here are purely from the processing that's being done within the algorithms that process what the raw data was captured into the display data that we're trying to see here. We move up over here, and you can see once again, the scout says that the cornea is a little bit steeper in the middle of that circle than the pentacam says. Down over here, once again, we have that sort of downward-shaped triangular flattened area that doesn't seem to be present on the pentacam. And most interestingly, you can see that the steepest portion, or the most curved portion, on the scout is a bit higher up on the image than it is on the pentacam, as well as the overall shape is considerably different. So these changes really can make a difference in how Wave is going to use the template to then design up a lens. And this can be feeding you data that alters your thought process to design possibly error into your lens design. So let's take a look at these displays. So here's the curvature, elevation, and refractive displays on the pentacam. In the upper left, that's a curvature display, and in the upper right, that's the elevation. And by far, these are the two most important displays. You can see that there's the polka dot patterns down at the bottom there because that is extrapolated data, but we're not going to even talk about that area. We're going to talk about the area that actually captured data for a moment. So that little black circle right there is indicating the very thinnest portion of this cornea, and it's in the same exact location on all four of these displays. So we can use that as a reference. Now, we notice here on the pentacam upper left display that that area that's sort of orange is the greatest curvature of this particular cornea. If we look at the elevation, however, we could see that the greatest central elevation is considerably higher than where the greatest curvature is. Additionally, that area that's in the blue is depressed, and that depressed area is actually corresponding to the area of greatest curvature. And so what does this teach us? This teaches us a very, very important concept that cannot be forgotten, that curvature does not equal elevation. The steepest portion of the cornea is not necessarily the highest elevated area of the cornea, and in fact, often they are not at the same location. Elevation is going to be the relationship between the back of your lens and the front of that cornea, the anterior surface of the cornea, where curvature has to do with what's actually happening instantaneously at that spot and how curved the cornea is. Elevation is much more important in designing a lens for fitting issues than curvature is. And it's important to remember that those two are not the same and often can be very, very different areas of the cornea that you're looking at. So now, Wave imports the data, and here we have that same keratoconic, and this is the raw data from the topography of that particular cornea. On the bottom, we could see again the raw data that was collected by the pentacam, and these are the two exact same corneas, separated by about 5 minutes of test time. Extrapolation adds in peripheral reference data from where we didn't actually capture any data. You can see I did a little bit better job on the pentacam getting more peripheral data than I did on the Scout, and that's not uncommon that the camera can get out further than the Placido disc-based technologies can. Wave tends to smooth out the data that's coming in to represent what the corneal shape really looks like from the raw data that was actually captured. So let's see what happens to that. So on the left, we have the scout image of raw data that was captured by the topographer, and on the right is the cornea being represented in wave by what it thinks the cornea looks like. And you can see there's a very, very strong correlation between the two, but they're not exactly the same. We can see things have been a little bit smoothed out on the corneal representation in wave from what was going on the raw data. If you do remember back to my initial capture, this little divot over here was artifactual, and you could see wave actually got rid of that in importing the data. And again, this goes to why the whole DOTS editing process really is a considerable waste of time, because the data ends up being changed as it's being brought into wave anyway. And wave does a pretty smart job of smoothing things out in the correct direction rather than you spending time connecting the dots. Now, the Pentacam, we see, has also changed the raw data. For example, we can see that the raw data shows a considerably flatter area up here than wave's representation of that. So we can see that once again, the algorithm that brings in the data from the cornea to the topographer changes some of the data. And then when we bring the topography data from whichever instrument you're using into wave, wave further alters that data to some degree. Now, I don't think you have to be any expert topography analyst over here to see that although I have the same exact cornea that were measured by two different devices, wave thinks we have something of two different corneas. These really do look considerably different. Furthermore, wave believes that there's about 3.5 diopters of cylinder on this eye, where there's about 5 diopters of cylinder on this eye. So again, some of these algorithms processing changes that are made to the raw data are fairly significant. They are not just trivial, oh, well, it's cleaned it up a little bit and let's move on with our lives. We do have to be aware of what our instrument is doing. Furthermore, if you take a look out here in the periphery, you can see here that we have wave representing sort of like a royal bluish color, yet the royal blue kind of ends over here and we're down more into the blacks all out at this ring, which happens to be that diameter of that particular lens that I was using for this demonstration. And so wave believes that the image being fed from Pentacam is actually a little bit flatter out in the periphery than the image that is being sent in from the scout topography. And so this will play a role in how you design your peripheral curve system on these lenses and can change dramatically how the lens actually lands on this particular eye. Now, an interesting thing is that you'll notice that the scout image over here and the wave image over here look very similar, and the reason is because in wave's early days, the curve scales were identically matched. So every curve that's represented by whatever color that's being done in the absolute scale on the scout topographer are the exact same curves that are being represented on wave's interpretation of the cornea. And so it makes it very easy to be able to see the difference. Now, other topographer scales, they're fairly close to the absolute scales, but not exactly the same. So you do have to be aware of the color differences. For example, Pentacam represents the very flat areas with this purple color, which wave does not have. It represents it with this black. So, Medmont is also a little bit different in terms of its absolute display. But the absolute color display for the topographical map will be the closest one to the corneal interpretation that wave displays on its color map. Different topographers will create different reference data for wave, and we did see that in the fact that we have a much quicker flattening out here on the Pentacam data than we did on the Scout data. So what does that all mean? Well, I just brought up two lenses here that are default lenses. I didn't do any designing whatsoever. I just brought the two raw images in. Here you can see on the left, this is the Scout image and the cornea that's being represented. And here is the pentacam image with the cornea being represented. And that is being represented by this flat green line. You can see that the black line representing the back surface of the lens is displaying very differently on these two screens, despite the fact I've done nothing to change them. These are both the default lens. And the reason for that is it's not the black line is so different, it's that the reference for the green line is actually in different locations in space. And so the difference between the green line and the black line, how much space is in between these two, are going to be represented differently. We can also see the back curvature of the default lens, which is this lower left image right up over here. On the Scout, we've ended up with a much steeper, we have actually a steep reverse curve looking area on this default lens on the left, whereas the Pentacam thinks that the cornea was a little flatter, and so as a result, it's come up with a slightly flatter design on its default lens. So bear in mind, these two corneas were the same exact cornea measured by two different devices, and we've ended up with two very, very different models within Wave. And as a designer, looking at this Wave screen, if you don't understand how your data got in here from the various device you're using, whether it's the Scout, the Medmont, the Pentacam, the Keratograph, it doesn't matter which device you're using, understand that that is coloring, pardon the pun, but coloring the data to some degree and changing that data so that the template that you're referencing can be a little bit different. So now let's take a look at a case. And this is a really interesting case. It presented to me, this is 10 years ago. And this here was a 48-year-old white female, 25 years of uneventful soft contact lens wearing, basically unhappy now because she's a presbyope. She had been seeing her prior OD for 6 months and went through various onslaught of presbyopic options in her soft contact lenses, none of which worked. That OD had given up on her and referred her to the ophthalmologist to find out why she can't see well, and the ophthalmologist diagnosed keratoconus. Spectacle RX was -8 and -875 -0.5, axis 176, so she's a high myope. And she was currently in the soft lens multifocal 775 and a 750 with low ads on both because she is only 48 when she presented to see me. Now, when she came to see me, she was about a week after she had been to the ophthalmologist who diagnosed her with keratoconus, and yes, you guessed it, she went home and checked out with Dr. Google what is keratoconus, and by the time she saw me, she was a wreck, totally panic-stricken. She was going to go blind from this corneal disease that she didn't know she had. All she thought was she was dealing with presbyopia. I refracted her at -7.25, -1.25, and a 775 -1 with a 1 ad, which made reasonably good sense given her previous numbers that she presented with here. And I told her that this isn't keratoconus. I've seen enough keratoconus to know this is not keratoconus. This is corneal warpage. But I left the question mark there because she was a nervous wreck on this. And so I said, well, maybe it's keratoconus. Let's follow it and see what happens. I believe this is all soft lens-induced corneal warpage. So what was my management plan? I went ahead to her and I said to her, I said, listen, I'm going to put you into a different soft lens, and this soft lens is going to have a lesser of a modulus, and let's see if we can alter what your corneal shape looks like. I'll see you in a couple of weeks. And she said, no, I can't wait 2 weeks to find this out. I said, fine, come back next week and we'll take a look and see what you look like then. So she came back a week later at her 1 week follow-up. The top half are the original topographies and the bottom half are the new topographies, and you could see not much has changed. They look very, very similar. So we have corneal warpage, or is it keratoconus for real? I told her, this is corneal warpage. Go away. Please come back in 2 weeks. So that was my management plan. She came back 2 weeks and listened to me. And so this is 3 weeks now after I'd first seen her. And we can see now that the keratoconus is magically improved. Now, anyone who's taken care of keratoconus knows the keratoconus never improves like that. And so I was able to convince her that she really does have corneal warpage, and this really is a soft lens-induced problem, and this is not the corneal disease that she was told that she had had. And so she can relax and be calm. So what was the management plan? Well, she was reasonably happy with her soft lenses. She was just scared out of her wits that she'd had this disease. So I said, listen, since you seem to be improving in this new lens that I have you in here, why don't we leave you in this, and I'll see you back in about 6 months or so, and we'll see where your cornea is at that point. So she came back 6 months later, and lo and behold, we can see that there's even been a little bit more improvement from the time when I had originally seen her 3 weeks after meeting her on those bottom maps there. So I said to her, I said, listen, this isn't really normal looking, but it certainly looks a lot better than when I met you. And so let's go ahead and continue with this. She came back 6 months later for her comprehensive exam. And we can see that the maps from that day are on the bottom, and her eyes look considerably worse now than they did 6 months earlier. Especially on that right eye, there's a lot more peripheral steepening in the vertical meridian. So we saw the increase in corneal warpage. I had a very serious conversation with her. I said, your lenses, I know you're not symptomatic, but your cornea is complaining, and we can see that here on these maps. Let's get you fit into a gas perm lens, and I believe we can resolve this corneal warpage. Now, I know that there's a preponderance of belief that GPs alter every single cornea that they touch, but that has not been my experience. So we had a very lengthy talk about how to proceed, and she was very concerned with finances, so I convinced her to come out of her soft lenses altogether for 1 month, and then we'll see where her corneas were at. So she discontinued her soft lenses for 1 month, wore glasses begrudgingly, and she came in a month later expecting me to fit her. So no soft lens wear, and lo and behold, the bottom maps are still showing corneal warpage. To those of you who think that soft lenses discontinued for 3 days lets you get back to a virginal cornea, I hope you take notice of something like this, because you really can be fooled considerably. All right, so corneal warpage is improved, but it still is not resolved. She was very unhappy by what I told her next, because what I told her next is go away for another month, and let's see what your corneas look like after another month of no soft contact lens wear. And so she came back another month later. This is now 2 months with no soft lenses, and for the first time since I met her, her corneas look almost normal. There's still a little bit of warpage down there, but they look close enough to normal that I told her I can certainly design a lens from that. So let's go ahead and design up some new lenses, since I know you're miserable wearing those glasses that you have. So we move forward. These are the pair of multifocal wave lenses I designed. I put them into Optimum Extra Material. I did a GSIM design. It's a multifocal. I'm not going to get into the nitty-gritty of this design because that's not really the focus of this particular webinar. And we had her back for her 2-week follow-up. Now, interestingly, I don't normally do topography on follow-up like that. However, I had some externs with me in the room, and we were talking about this case and how we ended up moving her from a 25-year soft lens history into a pair of GP multifocals. And they were curious. They said, well, isn't the GPs going to cause warpage? So we took the lenses off, and I took topographies immediately after removal, and those were the ones on the bottom. And the top half are the ones I fit her from, and if anything, she's actually even more normalized now that she's been wearing the GPs. So we moved over 9 years later, and you could see this was just actually last month. She was just in. She's now 58 years old. She's been a 9-year GP multifocal wear, and I've done a couple of changes on those to address the advancing presbyopia. We had a comprehensive exam. She came in wearing the lenses. I took them off, and the bottom maps are the maps that I took immediately upon GP removal. So GPs don't necessarily have to warp corneas, and soft lenses are not innocuous to corneas. So she has normal corneas, so let's take a look The focus of this lecture is topography. So we take a look. That's tainted data secondary to contact lens wear from a soft lens. After 2 months of no lens wear, it was almost normal. And so that was much safer data to use to design a lens. GPs, we certainly know GPs can warp the corneas considerably out of shape. However, this particular very warped cornea that looks almost like a keratoconic was just from a poorly fitting GP lens. I put her into a rehabilitative GP lens. She came in 3 weeks later, and her cornea looked much more normal, and I designed the lens up from that. That was a final lens. And yes, scleral lenses are not immune to this either. That is a scleral lens wearer, and I bet you might think that might be a post-LASIK patient that's wearing a scleral lens. But it is not. After 8 weeks in a corneal GP, this is what that eye looked like. So scleral lenses are not immune to warping corneas. Soft lenses are certainly not immune to warping corneas. And GP corneal lenses don't necessarily have to warp corneas. But the take-home message here is that you always have to be on guard when you're taking these topographies right from the outset. Is it possibly tainted data that I'm looking at because they're a contact lens wearer? All right, so the WAVE process. Remember, WAVE is a modeling system. Okay, we import that data stream, we create that digital mold, and we're going to base a lens design on that. We import that data. Dots editing, don't waste your time with that. Spend time on getting the good maps and not on processing and interpolating imaginary data and adding in dots and things like that. That really is a waste of time. So all before even starting a WAVE lens design, I've created this list. This is sort of a checklist, okay? The importance of good topography cannot be overstated as we went over in webinar 1, okay? The lids must be out of the picture. We need good tier quality. We need proper operator training. You must calibrate. The eyes must be aligned both directly along the visual axis, or in this case, the topographer's axis, the video keratograph's axis, as well as it needs to be at the correct plane when it's captured. The map should be repeatable. Take time and figure out which is the best map to use. Understand the impact of tainted data that's secondary to contact lens wear, whether it's a soft lens, a GP lens, or a scleral lens. Extrapolation is necessary. It ends up happening, but you must understand how that plays a role in the data that you're utilizing with WAVE. Critically assess the raw topography capture and decide if you've really captured good, reliable, accurate data. Understand your unique topographer's processing algorithms and how that is going to massage the raw data into something slightly different, so that when WAVE sees this is going to be slightly different data than the raw data that the cornea actually gave to the topographer. And then critically assess WAVE's interpretation of all this data. Because by the time it gets to WAVE, it can be significantly different from the way it was when it was raw data. Okay, we're pretty much done with the topic for tonight. This webinar series is really all about fundamental educational knowledge, so if there's any topics that you would like to see addressed, please submit them in the chat box for us so I can incorporate them into the future webinars that we're going to be doing. For webinar 3, I already can tell you that you will be in much better shape if you read Chapter 1 in the WAVE user guide. And that's for WAVE 9.30. That's the current version that WAVE is on. For WAVE resources, these are the private consultation services that I offer, and I have 5 options for doctors out there. This is basically for advanced learning. It's for non-FDA approved designs. It's for very complex designs, and it's going to be for designs that are way beyond the help desk that WAVE can supply for you. Okay, the first one is case by case. And that's sort of learn as you go. So as the case presents to you, you can employ me to help you out on that particular case. On the second option, we have phone help, and that's typically more targeted for a specific case or to bail out a specific case. So you have some specific topic that you really don't understand, or some cases really making you crazy, and you've already designed 19 lenses for and it hasn't worked out right. You may want to employ me for the phone help to see why the case is off the rails and how do we get it back on the correct path. One-on-one personal time, that's where we really spend a full day or 2 full days targeting specific weaknesses that you have, as well as what goals you want to achieve. For example, if you want to spend an entire day becoming much more proficient dealing with keratoconics, we will spend an entire day doing just keratoconus. Design and supply are really for non-wave docs. That's where I will do a case for a doctor who doesn't have wave. And then there are the DVDs from the Wave Winter Weekend that I had done a couple of years ago that really is a very, very good overview spread out over 16 hours of theoretical concepts and clinical applications for Wave, ortho-K, scleral lenses, irregular corners, etc. You can find all this at the website there in the lower right. That's on my website. And then from Wave, there's the waivers page, which is for clinical support, the concierge lens service, the user guide, the Wave Academy, technical support, and the iOS resource there. There's also these webinars. They do end up onto the resource page, as well as videos and events that are happening. And then, of course, there's the Wave users group that's online. Thanks a lot for coming out tonight and listening to the information. I hope it was very helpful for you and moving you forward in your practices. And I look forward to seeing you at our next webinar.